of the most fundamental forces in the entire universe, electric charge. It's the invisible power that makes a spark of static electricity. And yeah, it's also the same force that's powering the very device you're watching this on. So let's get into it.
So here's what's on the docket today. We're going to start with what charge is fundamentally. Then we'll compare it to something we all get, mass, to see how it's different. After that, we'll dig into the unbreakable rules that govern it. We'll look at how objects actually get charged up, and then we'll wrap it all up with the beautiful math that ties everything together.
All right, first things first. We've all zapped ourselves on a doorknob or seen our hair stand on end. But what is this thing we call electric charge really?
You know this one, right? You take a balloon, rub it on your hair, and bam, it sticks to the wall, just defying gravity. So what's the magic behind that? Well, it's not magic. That's electric charge in action, plain and simple.
Okay, so if we get a little technical for a second, electric charge is a basic property of matter, kind of like how things have mass. It's this property that lets tiny particles push and pull on each other, without ever actually touching. It's the secret sauce that makes that balloon stick. And really, it all comes down to one super simple, super important rule. You've got two kinds of charge, positive and negative. And the number one rule of the club is this: opposites attract, likes repel. That's it. That one idea explains so much.
Now, to really wrap our heads around charge, it helps a ton to compare it to something we deal with every single day, mass. Let's put them side by side and see what we find. Okay, this chart really breaks it down for us. With mass, right, it's always positive. And gravity, it's force, only ever pulls things together. It's always attractive. But charge, it's a whole different ballgame. It can be positive, negative, or even zero, which means it can push and pull. And this is huge. In a closed system, charge is always conserved. You can't create it or destroy it. Mass, though? Well, as Einstein famously told us, you can turn mass into energy. You see, charge isn't just this wild, random thing. It follows some really strict, non-negotiable rules. And if you understand these rules, you're well on your way to understanding electricity.
These are kind of like the personality traits of charge. First, it's a scalar, which is just a fancy way of saying you can add and subtract it like regular numbers. It's also transferable. It can hop from one thing to another, which is what happens when you get a static shock. Super important. Charge always comes with mass. You can't have a charge just floating around on its own. And like we said, it's conserved. The total amount of charge in the universe is always the same.
All right, now we get to one of the coolest, most mind-bending rules of the universe, and it's called quantization. This basically means that charge isn't like a smooth, continuous flow of water. Nope, it comes in tiny, individual, indivisible packets.
And just how small is one of these packets? Take a look at this number. That ridiculously tiny number, that's the charge of a single proton or a single electron. It's the fundamental Lego brick of charge. And you can't get any smaller. You can't have half of one or a quarter of one. This is the absolute base unit.
And this little formula, it sums up that whole idea perfectly. The total charge, Q, on anything is just some whole number, N, times that basic charge packet, E. It's just like money, really. You can have 1 cent, 2 cents, $10, but you can't have half a cent. Charge works exactly the same way.
Okay, so we've got the theory down. We know what charge is, we know its rules, but how do we actually do it? How do we get that balloon charged up in the first place? How do things become charged?
Well, it turns out there are three main ways to get something charged. There's friction, which is just rubbing stuff together, like the balloon on your hair. There's conduction, which is charging by touching. But the one I want to show you, because it's honestly the most fascinating, is induction, charging something without ever touching it.
So let's walk through this process. It's pretty cool. Step 1, we take a positively charged rod and just bring it close to a neutral sphere. We're not touching it, just getting it near. And just like we learned, the negative charges in the sphere go, "Ooh, I like that," and rush toward the rod, while the positive charges are repelled and run to the far side.
Okay, next up, all those positive charges that got pushed to the far side, we're going to give them an escape hatch. We connect the sphere to the ground with a wire. Think of the Earth as a giant sponge for charge. It can absorb a nearly infinite amount. So those positive charges flow right down the wire and away.
And here's the clever part. While that rod is still there, holding all the negative charges captive on the near side, we snip the wire. We remove that escape hatch. And just like that, those negative charges are trapped on the sphere. They have nowhere to go.
And for the final step, we just take the rod away. Now that nothing is holding them to one side, those extra negative charges spread out nice and evenly all over the sphere. And boom, we've got a charged sphere. And the coolest part? The rod never even touched it. That's induction.
Okay, but this is all invisible, right? So how do we even know a charge is there? We use this nifty little device called an electroscope. You can see, normally it's two little metal leaves just hang there. But when you touch it with a charged object, that charge spreads all the way down to both leaves. And what do like charges do? They repel. So those two little leaves fly apart. It's a super simple but really brilliant way to actually see the effect of this invisible force.
All right, we've covered what charge is, how it behaves, and how to create it. It's time for the main event. How do we actually calculate the force between these charges? That brings us to one of the great laws of physics, Coulomb's law.
This is the law that lets us stop just talking about the force and actually put a number on it. We go from saying it pushes to it pushes with exactly this much force. It's incredibly precise. And here's the magic formula. I know, equations can look a little scary, but this one is pure elegance. It simply says the force, F, depends on how big the charges are, Q1 and Q2, and how far apart they are, R.
Let's just pull this apart real quick. It's simpler than it looks. The part on top just means bigger charges make a bigger force. Makes sense. But the part on the bottom is the really cool part. The force gets weaker with the square of the distance. So if you double the distance between two charges, the force between them gets 4 times weaker. And that relationship, that's called an inverse square law. And guess what? It's the exact same rule that governs gravity. It's one of the universe's favorite patterns.
So, think about where we've been. We started with a simple balloon sticking to a wall, and we ended up with a precise mathematical law that governs the cosmos. It really makes you wonder, right? If these tiny, invisible bits and pieces follow such perfect, predictable rules, what does that say about the beautiful order built into our universe? And more importantly, what's the next big thing we can create, all by understanding these fundamental rules?